one of the things that we're going to do in this class is we're going to uh, learn about something called derivatives. And that's sort of like a really big chunk of this class. And we're not ready to describe what derivatives are yet, but I wanted to sort of give you a heads up as to sort of where we're going. Um, Basically, what's going to happen is we're going to learn how to take derivatives of very specific functions. And then what we're going to do is we're going to learn how to combine these different functions together in different ways to get new functions. And when we do that, that's going to change how the derivative appears. So we really need to talk about different ways that we can combine functions. Okay. So if I want to add two functions together, I, I want to talk about the name of the sum of two functions. Its name is going to be written like this: f plus g of x. That's a single function. And how is that single function calculated? You just simply take each piece and add them together like that. Okay. A new function we want to create is f minus g. That's the name of the new function. And the way we calculate it is we simply subtract the y values of each function. Multiplication, it's called the product. The name of the product, we just write it as f times g like this of x. And the way we evaluate it is we simply multiply the two y values together. And then for division, we write it as f over g of x like this. And the way that we just calculate it is f of x divided by g of x. Now this last one has a special condition. We are not allowed to have g of x be 0. Okay. So when we do derivatives later, we're going to learn something called the product rule. And that's how we handle the product of two functions, the multiplication. We also want to learn about something called the quotient rule, and that describes how we're going to find the derivative of a quotient of two functions. Okay. The big one for us, I think everyone is comfortable with those, but this composition is kind of a big deal for us. So the way composition works is we write as f composed with g like this. And the thing that you have to remember is when you're dealing with functional notation, things are kind of evaluated going from right to left. In other words, um, the input value is on the right, and then first we're going to do g to it, and then we're going to do f to it. So the way that this guy is calculated is you start with x, first you do g to it, so you take g of x, then you take that output and you plug it into f. This. Okay. So if I thought of functions as like little machines, it's almost like you have this x value first, you plug it into g, the output is going to be g of x, then you take that output and you plug that into f. And then what you get coming out is f of g of x, like that. That's the composition. So if you were to pretend that you go from here to here like this, then the notation would have f composed with g. And just remember that the g part's the inside part. Does that make sense to everybody? All right. So let's look at example 5. In example 5, we want to combine these functions together. So if I have f plus g of x here, what is this going to look like? That's going to look like 3x minus 2 plus x squared minus 4. Usually we um, we collect like terms. Collecting like terms means you collect terms that have the same power of x. So there's only one x squared term. There's only one x term. We have two constant terms, so -2 plus -4 is -6. Okay. When I look at this is a polynomial. There's no zeros in the denominator. There's no negatives under even square roots. So the domain is going to be -infinity to +infinity. That make sense? Let's look at f minus g. We're going to have 3x squared minus x squared minus 4. Again, I want to remind you, the thing we got to worry about is we got to distribute, right? So don't forget to distribute the negative. We're going to get 3x minus 2 minus x squared. This time it's plus 4. And when we simplify that, that's going to be negative x squared plus 3x plus 2. Okay. So again, this is a polynomial. Polynomial, no denominator, no radicals. Domain is all real numbers. Any questions? All right. So this guy's a product. We got to multiply the two things together. So it's going to be equal to 3x minus 2, and then x squared minus 4. So here's where we got to do that FOIL thing, right? So I mentioned FOIL earlier. FOIL means first, outside, inside, last. So we go the first, this is the outside part, this is the inside part, and this is the last. I just think of it as a double distribution, that's all, but students like this FOIL idea, I guess. So we now want to simplify, so that's going to be 3x cubed, that's going to be minus 12x, that's the outside, then the inside is going to be minus 2x squared, and then the last is going to be plus 8. Okay. You can rearrange it so it's from lowest to highest if you want. I don't know if I really care, but I guess I did it for the other one, so I'll do it for this one. 3x cubed minus 2x squared minus 12x plus 8. Again, this is still a polynomial. In case you haven't realized it yet, the domain of any polynomial is all real numbers, because you don't have zeros in the denominator, because there's no denominator, and polynomials don't have radicals. So for this guy, we got 3x minus 2 divided by x squared minus 4, right? But this is the first one where we have an interesting domain. So let's calculate the domain here. So for the domain, the issue is we have zeros in the denominator. So we want to make sure, we want to throw away all the points where the denominator is equal to 0. When you guys look at this polynomial right here, does this give you any special feelings? Okay, what special feelings does it give you, Alice?
Union.
I'm sorry?
Union.
Union. Oh, yeah. That'll be the final answer. I agree. That's too soon. You were going to say something, Alice?
You can factor out it, so it'll be x minus 2 times x plus 2.
Okay. How'd you know that?
It was just kind of in my mind. Like I kind of like those were like the concepts that I kind of memorized throughout the math classes. So yeah.
Good. So this type of stuff kind of happens a lot, and some students, they sort of mastered some stuff, and other students have different scenarios. So when I look at this, I recognize this is a difference of 2 squares. And when you have a difference of 2 squares, when you have something like a squared minus b squared, this always factors as a plus b, a minus b, like this. Okay. So in this particular case, when we look at this guy, we can see that this is a difference of 2 squares by just noticing this is x squared minus 2 squared. We want that to be not equal to 0. So this becomes x minus 2 times x plus 2. Or did I do it? X plus 2, x minus 2 equal to 0. Not equal to 0. So we know which points we want to throw away. X cannot equal to -2 and X cannot equal to 2. Right. So when we want to write the domain of this guy, let's say that you're not fully comfortable with the situation. You can draw a picture. I'm kind of a visual person, so I always like to draw pictures when I start to get confused. So this is -2 here, and this is 2 here. I want to throw away those 2 points. So when you graph it, it looks like this, looks like this, looks like this. Right? And then hopefully you guys can write that as -infinity to -2. Union, as Sagar was saying, -2 to 2. Oh, I should have asked him. Oh, well, it's too late now. Union 2 to positive infinity. Is this what you're going to say?
Yeah.
Yeah, good. Perfect. Is there any questions about this so far? I have a question for you. And I'm definitely not trying to pick on anyone here, but I saw in the chat box that someone wrote perfect square. And I hope you get, yeah. Okay, so you know this is not a perfect square. Do you know what a perfect square looks like? Perfect square looks like this. It would be something like something squared. That would be a perfect square. Yeah. Okay. I just want to make sure you knew that. In fact, I'll just erase this, but perfect. Just as a quick aside, let's say, what if I gave you something like this? What if I gave something like x squared minus 5 equal to 0? And I want you to factor. Is it obvious to you guys how to factor that? I'm just asking because this starts to come up as you work on more advanced problems. So what do you guys think? How do you factor that? What would you do, Sagar? You have any feeling? How do you factor this guy?
Oh, like squaring both sides, x square minus. Yeah, squaring both sides.
Okay.
Oh, sorry.
So
No.
I was going to use my difference of two squares situation. And what I was going to do is I was going to do x squared minus the square root of 5 squared, right? So then when I write it like that, I hope you guys can see this would be x plus rad 5, x minus rad 5. Does that make sense? Like, I know 5 is not a perfect square, but I could think of it as a perfect square by working with the square root of 5 instead of 5. And then it just factors that way. So, I mean, Catherine inspired me to talk about this, but I did want to talk about this at some point. So if you have x squared minus really any number, you could think of it as a difference of two squares by treating the second number as a radical squared. Okay, so, it's kind of cool, I guess. Now we get to the interesting examples. So at this point, I've already forgot what F and G were.
Excuse me,
yes.
Professor, do you mind switching captions?
Yes, I'm sorry.
That's no problem. Thank you so much.
Yeah, my bad. I felt like, let me see, hold on 1 second. Right now it's Kate, so Dana, here we go. The alarm went off too. I thought I could remember in the 3 minutes, 5 minutes. Okay. All right. Perfect. So 3x minus 2 and x squared minus 4. Okay. So when we look at this f composed with g, the idea, remember, what does it mean? It means first take evaluate G, take the output and evaluate F from there, right? So what we're going to do is we're going to say, okay, F, and then what we're going to do is we're going to just write G in as the independent variable. So in our case, G was x squared minus 4, right? So we're just going to put x squared minus 4 like this. And then we learned what we were working with the independent variable. We were talking about evaluating a function. Remember, evaluating a function just means plug the value into the function. So in our particular case, our f function is 3 times the input minus 2. And instead of writing x, we just write that entire g function inside for x. This will be x squared minus 4 like this. Okay. And then we got to distribute. So then this guy becomes 3x squared minus 12 minus 2. And that simplifies down to 3x squared minus 14. And the domain is all real numbers because it's a polynomial. Any questions, my friends? All right. Let's do this last one. So we got h of f of x, right? And we got to write down what f is. So f of x was 3x minus 2, like this. And then this is the first time we worked with h. So let's take a look at what h is. So h was 2 over 3 minus x. So this will be 2 over 3 minus, and then I got to write whatever I put in there. So this will be parentheses 3x minus 2. That makes sense? Now we need to distribute the negative like this. So we got 2 divided by 3 minus 3x plus 2. And that simplifies to 2 over 1 minus 3x. What did I just do here?
I
Is
think
it
that's
not,
5.
is it 5?
You're right. You're right. It's for sure it's 5. For sure it's 5. And then this time we do have a fraction. So for the domain, we know that 5 minus 3x cannot be equal to 0. So that's the same thing as saying 3x is equal to 5, which is the same thing as saying, or not equal to 5, I should say, which is the same thing as x is not equal to 5/3. So our domain is going to be from negative infinity to 5/3, union 5/3 to positive infinity. Like that. All right.